それではお時間となりましたので、ウェビナーを始めてまいります。私は大陽日産イノベーションユニットの山崎です。
こんにちは。同じく大陽日産の中村です。本日は大陽日産 Velo3D 社共催ウェビナーにご参加いただきまして誠にありがとうございます。
本日のテーマはこちらです。サポートレスによる燃料効率化の実現と題しましてお届けしてまいります。本日はお忙しい中ご参加いただきまして改めまして御礼申し上げます。
今回初めてご覧にいただく皆様、こんにちは。大陽日産は産業ガスメーカーとして世界各国で安定安全なガスとサービスを提供しております。現在金属 3D プリンター事業に注力しており、パートナーであるVelo3D 社のソリューションを日本のお客様に向けてご提案しております。前回のウェビナーではVelo3D 社と大陽日産独自のソリューション 3D プロについてご紹介いたしました。
はい、これも非常に反響が良くてですね、我々としても皆様 AM を実用化していく上でさまざまな課題をお持ちなんだなと実感した次第でございます。
実はこのウェビナー、前回から数ヶ月空いてしまったんですけれども、お客様からもっとやってほしいというありがたいお声をいただいておりました。
はい、その点はご無沙汰してしまいまして申し訳ございません。今後も頑張って定期的に開催してまいります。それではここで今回のポイントをご説明します。本日のポイントは2つ。サポートフリー造形、それから Velo3D の非接触リコーター、こちらを超小型発電機の基幹部品の造形事例を使って講演してもらいます。ところで中村さん、この2つは実は密接に関連し合っているというところはバッチリ理解されてますか？
そうですね。私自身Velo3D が最先端の AM とは聞いてはいるんですけれども、実は詳しい内部構造までは秘密にされてきたので正直よく分かっていません。
なるほど、そうですよね。私自身もここはベロに訪問して初めて分かりました。ただこれを見ればですね、なぜVelo3D だとサポートが少なかったりあるいは不要だったりするのか、彼らの AM のコア技術が分かると思います。以上、どうか最後までお付き合いください。
ここで進行についてご案内いたします。ご質問はこちらの Q&A を押していただき、日本語でご入力ください。発表の途中でもご入力いただけます。また後からでもお答えできるように、ぜひ会社名とお名前をご記入いただけますようご協力お願いいたします。後ほど質疑応答のお時間をご用意しておりますので、お時間の許す限りご回答してまいります。
なおこちらは匿名設定となっております。他の参加者の方には情報はご覧いただけません。この点ご安心ください。
本日の発表者をご紹介いたします。KW マイクロパワー社のエンリケ社長、nTopology 社のライアン・オハラ博士、そしてVelo3D 社のジーン・ミラーが発表いたします。
こちらの KW マイクロパワー社はターボジェネレーターなどのメーカーでVelo3D の AM 技術と nTopology 社の設計ソフトにより、これまでにない軽量で高出力の製品開発に成功しました。
本日の発表に関するご質問はVelo3D 社のジーン・ミラーと大陽日産山梨研究所の小山がお答えしてまいります。皆様のご質問お待ち申し上げております。
なお次回のウェビナーはVelo3D 式 AM の全工程に迫ると題しまして、受託加工メーカーとの協業により後工程を含むすべての金属 AM の課題を克服したという事例をご紹介いたします。最近サービスビューローですね、受託加工メーカーさんが 3D プリンタを新たに導入するというニュースが非常に多く出ていますので、次回はこちらをご紹介してまいります。引き続きよろしくお願いいたします。
それではお待たせいたしました。本日のウェビナー、サポートレスによる燃料効率化の実現をご覧ください。
Hi everyone. We at KW Micro Power are aiming to build the smallest, most powerful, and lightest generators for aviation and ground power. Obviously, the way we intend to do this includes a lot of 3D printing. And that is pretty much our goal. we intend on doing this, obviously, by combining the most powerful software package available with the best 3D printing capabilities that we have found. So this is my team that is helping me to make our generators as lightest, smallest, and most powerful as they can be. Okay, this is our 30 kilowatt generator that we're introducing soon, hopefully this year, by mid-year. In it, there is quite a number of components that have been 3D printed, and we'll get into that in a little bit. And our generator, this one here, produces 30 kilowatts. Its dimensions are about 15 inches in diameter by 30 inches long. It spins at 90,000 RPMs. It runs on diesel, Jet A, JP8, natural gas, and biofuels. So the part that we're going to be covering in this case study is the one that you see here at the front, and that is the generator case. Okay, 3 years ago, I had a big problem. I had a difficult part that nobody could make, and this was one of the key parts in my engine. So with that problem, I went to IMTS looking for a solution, looking for somebody that would save me, because if not, I was just going to have to redesign the whole thing. So I happened to run into an old colleague of mine, aviation consultant, very intelligent fellow that knows a lot about manufacturing high-end components. And I told him my problem, and he said, Enrique, if you're going to solve that problem, you got to go see Velo. They are the most advanced, most sophisticated 3D printing systems that I know of. I had not heard of Velo up until that point. So soon after, I headed on to Velo, and there I met Benny Bueller, the company founder. So I told Benny about my problem, and he said, let me get your information. We'll get someone to get in touch with you. Soon after, Zach Murphy, I think at the time he was the VP of partnerships for Velo. He contacted me. I told him about my problem, and I shared my information. And he says, let me take a look at it. I'll contact you soon. The short of it is that about a month later, not only have they come up with a solution for the part, they had knocked off 37% of the weight. And here you see the part. So, I mean, that just saved me. And we continue on our journey. And definitely at that point, I had become a big fan of Velo. So now that we have identified, the manufacturer for us, we also need and want to work with the best software package that can make me maximize each component. And for the next trick that we did with Velo, what you see here is an igniter system for our engine that previously was made out of 3 very tight tolerance Hastelloy components. So we were able to combine the 3 parts into one, and at the same time reduce the cost and reduce the weight of the component. So that was project number 2 that we did with 3D printing. Project number 3 is the one you're going to hear about today, and this is the case for our generator. So from our billet configuration, when we started thinking of, well, now we want to knock off all the weight that we can out of this part, we started thinking, what else can we do? What else is there anything else can we gain? Are we leaving anything on the table? And one of the great things that we could do was to cool it. If we could find a way of running fuel through that part, we would have a couple of gains. Not only will we bring the temperature of the case down, which in turn helps the generator, but we will put all that energy into the fuel, which downstream will help my combustion and make it more efficient. So that is the premises of what we intended to do: knock off weight and run fuel through it and cool the case and put all that energy into the fuel. And in order to do that, Zach told me, look, we're going to need to work with nTopology. And I said, who's nTopology? He says, well, nTopology is the most powerful software package that we know of out there that can maximize your design. So he put me in touch with Ryan O'Hara, who has been just brilliant in his work. And without much further ado, I would like for Ryan and Gene to take over and tell you what it is that they did with this part.
Hey everyone, I'm Ryan O'Hara. Happy to be here. Glad you could all attend. Hopefully you guys will get some good education or out of this. Let's see how things go. Let's see. So just real quick background on, hey, what's nTopology, right? And so nTopology, we were founded in 2017, or actually in 2015, and released our first product in 2017. And that product was focused on periodic structures. And then in 2019, we released our latest product called nTopology Platform. And the idea is that's a computational modeling software for design, simulation, and then advanced manufacturing. And so we'll touch on each one of those areas today. And the key differentiator for our technology is that in most traditional CAD or CAE tools, you're using boundary representation data. So that's like a SolidWorks or Dassault or Siemens. And the idea is that you have a patchwork or a quilt of needed to represent geometry, right? And then our fundamental difference in our technology is we're representing geometry as implicit math equations. And the idea is that instead of storing hundreds or thousands or even millions of these surfaces to represent geometry, we just have one equation, and we discretize that equation when we need to, whether that's for visualization or simulation or manufacturing, right? And then when we think about math and geometry, we can actually take fields, right? And we deal with fields in all our lives, specifically like fluid fields or stress fields when I think of a FEA or simulation background. And those are kind of all represented here below in this image. But we can take those and we can actually use those as modifiers. And we're going to talk about how we did that for a shelling example here. And then fundamentally, we provide a method to allow people or engineers or designers to like reproduce workflows, right? So in some ways, we've heard our software referred to as a visual programming software. We're not going to dig too much into that, but I will refer you to our website or YouTube if you want to like go down that rabbit hole to learn more. And I'd be happy to go with you too. So maybe we'll do that a little bit here now. Spoiler alert, Enrique came to us with a problem. He had a generator housing. It was basically a thick piece of material designed for traditional manufacturing, right? Probably a combination of multi-axis machining with some wire EDM, basically taking a big chunk of metal and then removing material to do that. And fortunately, when Enrique came to us, oftentimes we encounter designs where some sort of engineer, usually a really smart engineer, has taken their design and kind of optimized it for their manufacturing process. And then they often come to us and saying, hey, I want to take this to the next level. And we often say to them, hey, maybe you actually did a really good job of designing for your process. Maybe there's not as much help that we can provide to you. In this case, Enrique came to us a little bit earlier on in the design process, right? And we still had some flexibility and ways to improve this part. And it was real simple. Enrique had a heat problem, right? I have a big piece of metal. I'm only cooling it with air, but I have plenty of room to add some cooling. And I said, hey, I got a solution for you, Enrique, and it's super simple. And it's basically, we're gonna variably shell this part. We're gonna shell this part and we're gonna fill it with a big cooling volume, right? And then in this discussion, early discussion, Enrique expressed that, he has fuel available, right? And fuel is often used in aircraft instead of just being a parasitic device or source of energy, right? Often it's pumped throughout the aircraft to cool things down, right? And I asked if we could do the same thing in this scenario, and he said, sure, right? And so this is kind of the concept we came up with. We basically have a generator housing, and then inside that, we're just going to fill this with a big volume, and we're going to pump that fuel around. But in addition to adding this cooling volume, we're also reducing weight, right? So we took about 40% of weight away, right? And we replaced that with this cooling fluid. And then we'll kind of get into how we did that and some of the things we did in our software to gain confidence in the design. And I mentioned before, this is kind of a home run for our software. So in traditional CAD tools, oftentimes when you need to shell a part, it can be quite difficult depending on the complexity. And so when Enrique gave us this original design, I actually tried in SolidWorks in this scenario to actually shell the part. And I instantly got an error saying that there was the quilt work of boundary surfaces wasn't going to allow me to perform that operation. However, in our software, it's easy peasy. It's about a 1 to 2 minute setup and operation. And then the idea here is that we could actually take a field, and I'm showing an example here where we took a topology optimized part that is normally solid. We shelled it, but in this scenario, we actually used a stress field to variably shell this part. And then for Enrique's design, we actually, I basically have the shell being thicker at the top and bottom because it's the critical interfaces for mounting. And we preserved the geometry, and we kept it relatively thin in the middle. So effectively creating a monocoque structure. So with that said, kind of get to the goodies. The idea here is that we added almost 2 liters of fluid for cooling volume. In this case, it was going to be jet fuel. And then what we did is we were actually able to, in our software, run or take the geometry, the shelling operation that we did, and working with one of my colleagues, we ran an ANSYS Fluent simulation. We'll talk about that. But we basically were able to calculate the fuel heat transfer coefficient so that I can actually do a simpler model in the design phase of this quite quickly. And I can do that all inside of our software. Fundamentally though, what we did is we took the external temperature and we took it from being about 190 C or 380 degrees Fahrenheit. So basically really hot, right? Like creating an oven there. And then we actually were able with the fuel to cool it down, cool the exterior of the case down to about standard temperature and pressure, right? So which the fuel is at in its storage tank. And fundamentally, we're also heating the fuel, right? And I think Enrique can talk to this a little bit more in detail later. But the idea is that we can take that fuel by transferring that energy, we're conserving that energy, and then we're basically preheating the fuel so that it's going to combust more efficiently. So kind of a win all around. And then real simply is we took the internal geometry, and this is the ANSYS Fluent heat transfer simulation that we did, but we're able to calculate this heat transfer at the walls, and I was able to apply that as a boundary condition in our software. And just real simple, in this scenario, we took the part that has been shelled, we generate an FEA mesh inside of nTop platform, and then that's a surface mesh, and then ultimately this FEA mesh. And then in addition to modeling the generator, so in this case, at a 30 kilowatt generator, Enrique has said in the past he's able to achieve like about 95% efficiency. We assumed that about 5% of that was going to be waste heat. So about 1,500 watts we're applying as a source of heat inside of this. And that's based on that surface area. And we're actually modeling the heat transfer here now in our thermal solver. And then we're also modeling forced convection. So Enrique is using this generator to actually pass air to feed the turbine itself through to provide additional cooling, right? And then ultimately get some free convection. And when we set this up in our FEA problem, we end up with a thermal simulation. And the idea here is that, we're able to visualize, the heat load path in this scenario, right? So relatively simple. And the idea here is in our software, we have a series of blocks on the far left that represent, the different forms of the geometry that we're bringing in and transferring to implicits and ultimately into an FEA model. And then just a quick visual of what's going on inside of this part to get to where we were. So I think with that said, again, just want to reiterate, this is a huge, not only are we, in aerospace, right? If we basically, within a series of a few operations, we're dropping our mass by 40%, right? And I'm providing an exterior cooling or temperature drop down to, near static temperature and pressure. As in preparation for this, I think all of us, Gene and Enrique and we all talked about this. It's like, this is a real simple win. It's like, I made your part stupid light and I made it really cool. Like wash my hands, done, high five everybody and win, right? So it wasn't in this sense a terrible engineering problem, but it's really the culmination of bringing a need, right? Some advanced design, being able to do a relatively simple operation, you would think, called shelling, and then actually applying that here to this part, and then fundamentally manufacturing it. And with that said, I'm going to turn things over to Gene.
Thanks, Ryan. Hi, everybody. I'm Gene Miller, and here to talk about the fun part of this whole project is actually manufacturing it without the need for any type of compromise. The real big win here was to take all that work that Enrique did and all that work that Ryan did and say, yeah, sure, let's print it. You know, we don't have to go back to the drawing board. We don't have to compromise. We don't have to make any changes. So with that said, we're going to talk about, you know, a real high level. This is what a laser powder bed fusion system does. And in a conventional sense, you'll have a piston inside a cylinder that moves down a designated length of distance, and that's your layer thickness. In our case, it's about 50. It is 50 microns. And then in the middle here, you see what we call the recoder. And on a conventional metal AM system, the recoder, I like to call it a dump and smear method. It kind of just plows a bit of powder over the top of the part and leaves a thin thickness of powder to be melted selectively by the laser. And every layer, happens iteratively, and eventually it builds up to complete your printed part at the end of the day, and then all the unfused powder is removed and recycled. But that is essentially on a high level how a typical laser powder bed fusion system works. So in a conventional metal AM system, these challenging features that we have to overcome are supported. Supports are really, they're not there to prevent the part from collapsing or anything. They're actually there to keep things anchored down and constrained so that the internal stresses that are developed during printing don't cause deleterious warping and movement of the parts. If you look at the desired outcome on the left here, this is essentially what we would want to print, but without any support material, these overhangs tend to warp upward and can tear themselves apart and cause recoding to be impossible. So what the conventional solution is to add supports to these low overhangs. And that's what we're showing here in the red. These are support material that's added to the part. And that's fine if you can access that material and remove it after you're done printing. And in this case, we have some really isolated volumes which are inaccessible after printing, and you just can't get in there to remove any of the support. So we can't put it there. But the good news is we don't have to. So here's a kind of a comparison between a conventional DMLS printer supporting scheme versus a Velo3D Sapphire. Everything on the left under 45 degrees has added support material added to it. And some of the areas are accessible in the center of this part, but the enclosed volumes that are inaccessible where there would be support on a conventional system just don't make sense. You can't get to this after printing, so it's, you're kind of printing garbage. The Velo3D Sapphire printer has no need to put support on these internal volumes. So at the end of the build, all you have to do is just remove the powder from these channels, and they're open and free flowing, and no need to add any support material. So how do we do this? It's kind of biting off smaller pieces and applying specific laser parameters to specific geometries in order to get a desired outcome without the need of adding support. We have our preprint software package that Velo3D designed. It's a preprint kind of a 3D space where the user can import a CAD part. They can orient and add support and then click prepare for build. Now Flow automatically recognizes all the geometries in this part and applies specific laser parameters to ensure successful printing without the need for added support material. In this case, for this part, we have certain geometries like closures. There are tall vertical walls. There are some low overhanging features that go below 45 degrees or even near 0 degrees. And then there's also some bulk core where you really want a specific laser parameter to put down as much material as quickly as possible to really enhance your print time. This discretization of laser parameters really helps us achieve unprintable geometries in other senses and really still be competitive as far as a throughput sense. So on a high level, here's how the support free is enabled by the non-contact recoder. We have a powder dispenser that kind of snows down gently a thick layer of powder over the substrate of the powder bed. Now, behind that is a normalizing blade that then flattens and normalizes that surface after it is dispensed. And then behind that, that's where the magic happens. That's our proprietary powder removal tool that comes in behind the normalizing blade and removes all but 50 microns of powder. So the net is the same. We still have a 50 micron thick powder bed each layer, but we never actually come in contact with the part. We don't have to worry about movement or interference with the recoder. So the Velo3D platform, we call it a full stack solution. There's 3 tiers of our product. First is flow, I mentioned that earlier, where the engineer takes their CAD or their design intent, brings it into a 3D space. They can orient, add support material if necessary, process overrides, and then actually prepare the print file. And the print file is what's taken over to the Sapphire printer, and that's where the real printing happens. That's where we recoat, we selectively melt, and print the part. Now, all throughout that printing process, there are literally thousands of sensors gathering data on this machine, and we needed a way to compile it in a really concise, graphical, friendly to the user interface, and that's where Assure comes in. Assure is our quality validation software. It's designed for real-time monitoring of the builds as they're being printed on the Sapphire machine, and also after the build, we produce a very concise, clear build report to validate the quality of the part. So going through this build in particular, it starts off pretty typical. There's some bulk material here, and where this little clip ends is at the beginning of the cavity as designed by nTopology. There's nothing really challenging about this yet, but this is where this part starts to get interesting. This is where we've got these open cavities as designed by nTopology. So moving upward from there, the walls are pretty thin. They start to get pretty tall, especially these internal bosses and tubes can be subject to recoder interference. As they get very tall, they get flimsy, and any lateral force could move that thin structure around. And on a conventional metal AM printer, that might be problematic. It's just something that we don't have to worry about because of that non-contact recoder. Then lastly, these internal cavities close out without any added support material. Again, they get a specific laser parameter so that we don't have any real degradation of surface roughness at that closeout, as well as no need for added support material that in this case would be impossible to remove. And here's the printed part. This is right out of the printer, ready for final machining. This part was about 9 inches round by 9 inches tall. It's printed in aluminum F357. The overall print took just under 3 days. It was about close to 5,000 layers. And there's this line that you see here is an artifact of the internal closeouts and internal passages, kind of causing a difference in thermal history, but it's all cosmetic. We were really pleased with how this came out. All the internal passages are free flowing and able to do exactly as intended by Enrique and Ryan. And now I'll hand it back to Enrique to kind of summarize what we talked about here today.
Basically, the message here is design without limitations. What I call it is a great opportunity for today's engineers to really be able to go back and look at everything and see, can I do it differently? Not just knock off weight off of it, but is there anything else that I can gain? Can I put a probe here? Can I put a sensor there? What else can I gain? And when you start looking at every part, then you see games all over the place. Like, for example, we're going back to the drawing board. There's more work to be done with nTopology and Velo for me, as you can imagine. So I'm a glutton. I want to completely devour this opportunity. So for the rest of you engineers out there, it's what I call a renaissance of engineering. You just go out there and look at a part differently. Now you're not limited by the conventional machining methods. And that's my message.